So basically a prime number is just kind of like any number that only has two factors, right? So a prime number has two factors, right? And then the two factors are one and itself. So like, and prime numbers don't have any other factors, right? So like prime numbers can only have two factors, one in itself. So for example, like the number 7 is a prime number because the only factors of 7 are 1 and 7 itself. So 7 is a prime number. However, like the number 9, on the other hand, this is not a prime number. This is not a prime number because even though 1 and 9 itself are both factors of 9, 3 is also a factor of 9. So like this kind of, since you have 3 factors here, it kind of violates the 2-factor condition, which is why like 9 is not prime, while like 7 is prime. So remember that like in order for something to be prime, there has to be exactly 2 factors, one in itself. And like the numbers that are not prime, like in this case 9, we call them composite numbers, right? So like we say 9 is a composite number if it has like more than 2 factors. Of course, you have to be careful. Like composite isn't like the opposite of prime. Like just because a number is not prime doesn't mean it has to be composite. Like for example, the number 1, it turns out the numbers 0 and 1 are both like kind of like exceptions. Like 0 and 1 turns out to be like neither prime nor composite. Neither prime nor composite. I just wanted to like quickly say that because like I know a lot of people like get confused and they wonder if like, you know, if 0 is prime, if 1 is prime, and a lot of times that's like a question that people have. And yeah, so this is kind of like the definition of a prime number. So prime numbers have lots of interesting properties. So it's also very important to like be able to identify whether or not a number is prime, right? So like if you wanted to like see whether or not a number is prime, like for example, let's say we want to check if 9 is prime. Like one way we could do it is we can just check all the like positive integers and see if they're factors of 9, right? So you first look at the smallest positive integer 1. Is 1 a factor of 9? Like yes. So like that's normal. Like any number is divisible by 1, so you can move on. Then you look at the next number 2. You step up one level. Is 9 divisible by 2? Well, no, because like 9 is an odd number, 2 is an even number, 2 is not a factor of 9. Then you check 3. Is 9 divisible by 3? Yes, 9 is divisible by 3. So since 9 is divisible by 3, we know that 9 is composite. Because remember that the only factors of 9, if it were prime, are 1 and 9. But since we already found a factor that's not 1 or 9, then we know 9 is composite. So let's try like a slightly more complicated example just to like better understand what I'm talking about. So let's say we want to check like, is 35 prime, right? Again, the most like intuitive way to like check this is we can start from 1 and gradually build up and check like the positive integers from 1, 2, 3, 4, 5, and so on. So we first check 1. Is 35 is 1 a factor of 35? Well, yes. Like 1 is a factor of anything. So then you move on to like 2. Is 2 a factor of 35? No, right? Because 2 does not evenly go into 35. Then you check 3. Is 35 divisible by 3? No, because like, you know, 35 divided by 3 is non-integer. Is 35 divisible by 4? No, with like the same reasoning. Then you can check, is 35 divisible by 5? And like we clearly see 35 is divisible by 5. So since we kind of found a factor of 35, in this case 5, we can immediately stop and say 35 is composite, right? And this method of like kind of just checking the numbers one by one, like start from 1, then check 2, then check 3, then check 4, until eventually you find a number here like 5 that works, then you can conclude that it's composite. Like that is one way to do it, but like if you get to like really large numbers, right? Like let's say you're checking something like 323, you for sure don't want to check the numbers 1, 2, 3, 4, 5 all the way up to 323, because that would take a very long time, and you don't have that much time to like check whether like this is prime or not. And similarly, like, and let me like also finish this part. Like if none of these numbers worked, right? Let's say we wanted to check if 17 is prime. I should have like talked about this before I moved on. Let's say if we want to check like if 17 is, or let's say a smaller number like 7. Let's say we want to check if 7 is prime. Like what we would do is we would start at 1. We see 7 is divisible by 1, so that's normal. Then we know that 7 is not divisible by 2, right? 7 is not divisible by 3. 7 is not divisible by 4. It's not divisible by 5. It's not divisible by 6. It is divisible by 7. So we checked all the numbers from 1 through 7, and we found that its only factors are 1 and 7. So we know 7 is prime. So like just to summarize, like our like intuitive way to like check if a number is prime or not is just to check all the positive integers up to that number. So like in this case 7, we would just check all the numbers up to 7. And if the only two possibilities that divide 7 are 1 and 7, or like in general, if the only two factors that divide this like number is 1 and that number, then we know it has to be prime. But like, as we can clearly tell, this can get quite tedious, right? So as with the example, as with the example, like if 323 is prime, right? Like for sure, we don't want to check all the numbers from 1 all the way up to 323. We don't want to say, okay, 323 is divisible by 1. That's good. And then you check 2, it's not divisible by 2. We check 3, it's not divisible by 3. You check 4, it's not divisible by 4, and so on, right? That'd be kind of like tedious. It would be like a lot of numbers to try if you wanted to try all the numbers from 1 up to 323. So what we're going to talk about is like kind of a quicker way to kind of test if 323 is prime or not. So it turns out, right, like we only have to actually check the prime numbers, because let's say we found 323 is not divisible by 2, right? Let's see, we know that 323 is not divisible by 2. Then that means we don't have to check any other number that is a factor of 2. We don't have to check if it's divisible by 4, 6, 8, 10, and so on. Because if 323 is divisible by 2, for example, then there's no way it can be divisible by like a factor of a multiple of 2. Like if like for example 4 here is equal to 2 times 2. So if 323 is not divisible by 2, then it clearly cannot be divisible by 2 times 2. Like that'd be like even a stricter value. So that tells us that we actually only have to check the prime numbers up to 323, for example, if we wanted to see if that's a prime number. So that means we don't actually have to check all the numbers from 1 to 323. We can check like only the prime numbers. Like we can check 2, then we check 3, then we check 5, then we check 7, then we can check 11, and so on. So we just have to check all the prime numbers and see if they're factors of 323. So doing this allows us to skip slightly more numbers. But overall, this still can be kind of slow if your number is really large. Like let's say you want to check if like 997 is prime. Like still, even though you don't have to check all the numbers from 1 up to 997, there's still a lot of prime numbers from 1 to 997. So this way is not exactly like that efficient. Like it's still kind of slow. So it turns out we can kind of make like one more optimization. And when I say optimization, I just mean like just making it faster, this algorithm kind of thing, which is the observation is to notice that if you have any number n, right, let's just say we have like an arbitrary number n, if it can be written in the form a times b, where a and b are positive integers, then at least one of a and b has to be less than or equal to the square root of n, and at least one of them has to be greater than or equal to the square root of n. So it might have been kind of confusing, so let me give like an example. So let's say we had like 16, right? We can write 16 as, or let's take like 36, for example, actually. So 36 is a perfect square, right? I can write 36 as equal to 6 times 6. Now, notice that if I were to write 36 in any other way as the product of two numbers, like if I said 36 is 1 times 36, right? I can say 36 is 2 times 18, 36 is 3 times 12, and so on. Notice that like all of these numbers, like let's take a look at this this red equality here. Notice that exactly one, like 1 in this case is less than 6, and 36 is greater than 6. So, and let's take a look at like this green one now. Like 36 is 2 times 18. Notice that 2 is less than 6, and 18 is greater than 6. So in general, if you have 36 equals A times B, then you're going to have A is less than or equal to 6, and B is greater than or equal to 6. You can kind of think of 6 in this case as kind of being like in the middle, like sort of. So like, because, you know, if you had like 36 is 2 times 18, like exactly one of these numbers is going to be less than or equal to 6, and the other number is going to be greater than or equal to 6. And this is why, since n is equal to square root of n times square root of n, it turns out we only have to check up to the numbers all the way up to the square root of n, because if there existed a factor that was greater than square root of n, then that means we also must have a factor smaller than square root of n by this like reasoning here, which is why we can like significantly reduce the number of positive integers we have to test, and instead only try up to the square root of n. Yeah, so let's just take a look at an example. So let's just apply this kind of to like an example. Like, let's just take this example, right? Is 323 prime. So using like our new algorithm, like we noticed that like the square root of 323. So you basically, you first take the square root of the number and you approximate it. So the square root of 323 is like between, it's going to be between 17 and 18. And the reason why is because 17 squared is less than 323, which is less than 18 squared, because 17 squared is 289, and 18 squared is 324. So 323 is between 289 and 324. So if we were to take the square root of both sides, we would get square root 323 is between 17 and 18. Just a brief intro there. So that means like we only have to check all of the prime numbers from 1 up to like 17 or 18. So that means we only have to check the numbers 2, 3, 5, 7, 11, 13, and 17. So now notice that we only have to check 7 numbers, 2, 3, 5, 7, 11, 13, and 17, as opposed to 323 numbers. So we like greatly reduced the number of possibilities that we have to check. So let's see, we can check, is 2 a factor of 323? Well, clearly no, right? Is 3 a factor of 323? This is also no. Is 5 a factor of 323? No. And it turns out you can check 7, doesn't work, 11 and 13 both don't work. And then when you try 17, it turns out that 323 divided by 17 does give you an integer. So it does give you 19. So that tells us that, you know, 17 works. 323 is divisible by 17. So that tells us 323 is composite. Yeah.